light. A light for the front.
Okay.
Can you turn on the board lights?
I also don't know.
That's fine.
Yeah, maybe that's fine.
This is good as well.
Alright. Continue.
But also the board lights. Don't want to be able to see that well.
It looks good.
All right.
Okay, so welcome everyone. Today we're very happy to have Bauer from EIS, who's going to be talking about the factorization problem in SYK and in matrix models. Bauer, please.
All right, thank you for inviting me to speak. It's a pleasure to be in Chicago for the first time. So I'll speak about the factorization problem. And this is a really problem that arises in gravity that we would like to understand in gravity. But I will present some today we will study it in some simple models of toy models of quantum gravity. So the basic problem in ADS-CFT is that suppose you have multiple boundaries, let's say 2 boundaries, living on some Euclidean time circles of some length, and then in the QFT side you would like to compute some products of partition functions, and then gravity instructs us to fill this in with all possible geometries, and then there are particular contributions from some wormhole-like geometries. And then you sort of get puzzled because from QFT perspective you get a product of partition functions, and it's factorized between different boundaries. But in the bulk, you seem to have these connected geometries, and it's at first glance, at least, it seems puzzling. And so, you might wonder what you have to do. I'm sure you've probably heard many talks about this, right? And I should emphasize that in Euclidean signature, this is never really a sort of sharp problem. In Euclidean signature, these geometries are always subdominant, comparing to, let's say, the disconnected contributions. But in Lorentzian signature, if you continue betas to Lorentzian signature, this becomes a sharper quantitative sort of paradox or problem. And so to study this problem, we sort of have a more sharp version of this problem. We can study, or people usually study, this spectral form factor. And in chaotic systems, you typically expect some profile that you initially decay, and then at some relatively long time, you get some universal features. Like this linear in time growth and then the plateau. And moreover, at these long times when you start sort of having this universal random matrix description, this sort of form factor, this starts fluctuating a lot in time. And these fluctuations are in fact comparable to the signal itself. Okay, and so people have studied this quantity in gravity, in particular in JT gravity, and Saad, Schenker, and Stanford, they show that some regions, like this linear growth region, has actually a simple description, at least in some toy models of quantum gravity. And in JT gravity, they show that it actually corresponds to computing precisely this kind of geometry and integrating over all possible connected geometries of this sort. It reproduces this linear growth once you continue to Lorentzian time.
Can I ask a quick question?
Yeah.
So people always say ADS-CFT tells us we just need to sort of fill in whatever geometries connect these disconnected boundaries.
Yeah.
But is there any setup where, I don't know, like take ADS5 cross S5, take like 2 stacks of branes or something, where I get just 2 decoupled copies of n equals 4 and I should somehow like have some connected ADS5 region connecting the 2 things? Like, is it clear that that's really what the rules tell us what to do?
If I understood correctly, you're asking if I should include these geometries in my computation or not?
Something like that has to necessarily correspond to just like 2 disconnected copies of like the CFT. Like, could there be, I don't know, some like mode that tells you like the overall sort of position of the 2 stacks of branes or something? Or like even taking the sort of near horizon limit, like how does one do that to just get 2 copies of sim or something? This is maybe not, we can also delay this question for later, but it's just like, is it totally clear that that's just what the rules say? Like
that these geometries should be included in the computation?
Yeah, basically.
Well, I think that's something that's debated, but it seems that these geometries actually give you a lot of interesting physical information. In particular, one thing is that they reproduce this thing, including the coefficient from the random matrix theory. They also replica wormholes and so on, and they reproduce quantitatively some interesting features that we would like to keep, and so it's better. It feels like we should keep them and try to understand it, because they are good for explaining things, and but then we need to understand this puzzle.
And I thought the mystery here is that the left-hand side exists if you just take two copies of the CFT, and it seems to correspond to that geometry. But then why wouldn't you include stuff that would violate factorization?
Well, I guess he will tell us that if you actually sum over everything in the bulk, it will still be factorized.
Oh yeah, I mean, but there has to be some explanation for why.
Yes, that's the goal of this talk, essentially, to say that in fact we should add some other stuff, and this other stuff would give you in the end factorized answer. Right, and so, and in fact, from this picture, it's kind of clear what we're missing. So this, there's this averaged signal where you either average over ensemble, or you can also average over some time windows, and then you get this smooth signal. But if you don't average, if you have actually this factorized quantity, you have this large noise. And it's clear that you cannot neglect it because it's of the same order. And so what essentially resolves this factorization problem is that you have to add this noise. And so the basic question is, what is this noise in gravity? Or can we even describe this noise in gravity? So on. And what I will try to argue today is that there is some sort of effective description of this noise, essentially, in some sense, which I will explain as we go forward. Right, so that's the goal, right. Yeah, so let's. So that's the setup. If there are any questions about the setup, it doesn't come down. So not. So this noise, it has been studied last year by Saad, Schenker, Stanford, and Yao in SYK model. Or even more precisely in sort of a simplified version of SYK, which I will describe later. But essentially, they found some sort of effective description of this noise. They found what's sort of I will draw a picture that looks kind of weird, but let me start with that. So they found some contributions that they called linked half wormholes. So the way they did it in the SYK model is that they noticed that in SYK model you usually average over the couplings, but they noticed that even if you do not average over the couplings, you can still introduce this sort of usual G sigma action, effective action in the SYK model. And then they studied this action with fixed couplings in the SYK model, and they found that one set of saddles are like this, like wormholes, but there's also another set of saddles if you do not average over couplings, and those what they called linked half wormholes.
How do you know if something is a saddle if you have random couplings that you're not averaging over?
So
saddle
those
means it solves an equation, right?
Yeah.
How do you check that it solves the equation?
They actually wrote an explicit G sigma action, which also depended on the particular couplings that you chose. And in that effective action, they found saddles that saddles that depend on the particular choice of the couplings that you have. So it's not the standard SYK G sigma action. It's somewhat modified by the presence. So I'm not going to describe this in too much detail today, but instead I'll present a sort of different approach which reproduces their answer from a different point of view, and which will also generalize to matrix models.
Before you go on, can you just briefly tell us, for those who aren't following this subject very closely, what is meant by this squiggly picture in the middle?
This picture?
No.
This picture?
Yeah. What is meant by the linked and the rough edge and so forth?
Right.
Is that really a geometry?
So the reason they drew them like that, or like called them half wormholes, is that so in this G sigma action, so you have, so if we call this system left and this system right, you have these G variables, which are essentially, so these G's are like some bilinears in fermions, in Majorana fermions of the SYK model. And on this half wormhole saddle, they are such, it turns out, that these G left and right fields are the same sort of as on the wormhole solution. So in the sense, sort of the correlators, one-sided correlators here are the same as on the wormhole. However, the G left-right variable is 0. So in this sense, there's no sort of correlations between left and right, but there are, but the correlations that are one-sided, they're the same as the wormhole correlations. But the reason they put this sort of, or call them linked half wormholes, is that this G left-right, this variable is still present in the path integral, but you set it to 0 on the saddle.
Does there exist a smooth geometry which is dual to this configuration of fields?
Probably no. So this is a sort of a proxy for what happens in the bulk. So this is actually not the picture that they found in the bulk description. It's just something that seems like it corresponds to that. I will. This will also have a different interpretation from the approach.
Okay.
Right.
The link means what? It just means, what does the link mean?
So in this approach, the linked means that there is G left-right variable in the path integral, that it's present in the full path integral that they write, but on the saddle it is 0. There could be a different description of the path integral where you sort of work, let's say, in just the Majorana fermion variables, right? And then in that description, there is no fields that sort of correlate the left and right boundary, and then it's explicitly kind of factorized in that description. And
I'm a little confused because you have a first term, right, which comes from the naive saddle, where there is such a there are such contributions to the 2-point functions. So how can you cancel off a non-zero correlation with something that is factorized?
this thing is not factorized because it's
But it makes G left right equal to 0.
On the saddle, but there's
on the saddle.
there's some determinant that's somehow important.
Okay.
Right, so this is roughly this picture that they had in this paper. And one important fact about it that I should mention, this equation essentially is that if we compute the square of the partition function with some fixed set of couplings J, then one term is the wormhole, where you average over the couplings. That's the smooth contribution. And the second contribution is this linked half wormhole contribution. And so the important fact about this equation that they wrote is that it's not sort of an approximation in a regular sense. Instead, it's an approximation for a typical choice of the couplings J. Okay. So what do I mean by that is that if you take the difference of the left and right hand sides, so this is something that depends on the couplings, and then the average of this error is 0, and the variance of this error is much smaller at large n than the form factor itself. So it's a good approximation, but it's a good approximation for a typical choice of the couplings J. But if you try really hard, you can always find some weird couplings for which it would be true. For most choices, it is true.
So Z is the spectral form factor at some coupling.
Yeah, Z of J is J are fixed couplings.
And it also depends on T beta plus IT, but
here put like see them that much.
and there's also a beta, so it also depends on beta plus IT.
Yeah. Here I just emphasize the dependence on the coupling.
But you'd expect that the error depends on the time, right?
Yeah, the error will depend on all the temperatures and times.
Like at early times, it's self-averaging, but not at late times.
That's right, but we will, Here, I guess I'm not very much interested in very early times. I'm interested. So, right, in gravity, you can actually, you can imagine also doing this computation of this sort of variance in gravity, right? And so we discussed before that, so the average of Z squared is kind of this wormhole. But now if we do not include this extra term, and we try to compute the variance of this difference, right? So we would need to compute this Z to the 4th, and there will be 3 contributions at leading order, which are just disconnected wormhole geometries. So that's z to the fourth to the leading order. And so if you now also subtract, to compute the variance, if you subtract z squared squared, then this term will say cancel, but these other two will remain, and the variance will be 2 z squared squared. And so if you don't include this extra term, the variance is large. And so the whole point of this approach is that we find this something extra such that this variance is going to be small on average.
And the totally connected 4-point is just even further subleading it.
Yes, right. That's some more something at large. Oh, I guess this doesn't move. Okay.
Well, not the back one.
Right. Okay, I guess. It's okay. So now let me describe how you actually get some complete formula for this extra piece. So the sort of basic idea is very simple. So the basic idea of the approach that I would like to take is that we would like to compute something with the fixed couplings. So obviously we can, so now we would like to first write it in some way that kind of imitates that there is an ensemble. So sort of a trivial identity that we could write. Just that we insert the delta function, and we insert some potential, which will later become like ensemble energy. Now so this I will just say roughly how it works in both the SYK and matrix model, and then we'll consider it in more detail. Right, so we can introduce another variable here. Let me just say it like that. So this delta function, well, you write it as an integral over the second variable, and then the integral over j's becomes like an ensemble average. And what you're left with is a sigma integral where you average z of j squared in the presence of some external field. Okay, and you have some factors here, right? So this is just a trivial rewriting, if you wish. But now what I would like to ask is there sort of a meaningful approximation that we can make here that looks like the one I described on the previous points? And so the claim would be is that now if you compute this average, and let's also normalize it for good taste, then the claim is that at large n, two contributions will be precisely as I described before. So one of them will be when two z's are correlated with each other. So you just have a form factor. But then there will be a second contribution when two of z's, they are correlated with this external field, but not correlated with each other. So in that case, you consider a contribution where you have two factors where two partition functions they're sort of talk to each other only through this external field. Well, you might ask, well, you might be confused. Why do I consider such an approximation?
Sorry, the approximation was in what expansion?
Right. So, that's a good question, and that's related to my comment before that the approximation with the half wormholes was valid for typical choice of couplings, right? So
same sense here.
yeah. So what I will show is that this approximation is actually giving you that description that I told you about for a typical choice of the couplings. And the fact that they're linked here is because you have this sigma integral, and they talk to each other only through this channel.
Can you just expand Z in a bunch of phases and try to, like, is that the strategy to identify which terms, like Z is a looks like e to the I times the eigenvalues, right?
Yeah.
And typically they cancel, but like in Z
You mean
squared.
that Z is just trace of e to the minus.
Right. Yeah. Is that the strategy? Like you try to expand this and eigenvalues and.
Well, in the examples I will consider some like simple examples like SYK dot and Gaussian matrix models and so on, and I will compute it explicitly and show that it works. But the conjecture I think is more general.
So when you say you compute it explicitly, you have a way to compute it without assuming that J is typical, the coupling is typical.
Oh, no, what I meant is that I can explicitly compute this object and then check that for a typical choice of the couplings, it's a good approximation. So that's the idea. And right, so, well, yeah. Well, the reason I wanted to look at this is that, I looked at the G sigma derivation that Schenker, Stanford, and Yao gave, and I guess I was confused, like how would you generalize it to other models, for example, to matrix models. And I thought it'd be nice to have a description of this in matrix models, because with matrix models we know better sort of how they sometimes describe quantum gravity, that they're dual to a minimal string and so on, and that perhaps you could understand the bulk better if you understood matrix models instead of the SYK where you sort of don't have a good bulk description. And we're not there yet, but nevertheless, I will describe what I have found in matrix models in a bit. But before that, I guess I'll. How much time has passed? Let's see.
We started like 10 minutes late. So.
Like half an hour still.
I have like half an hour. Okay. Right. That's as usual much slower than I expected, but let's see what I want to do. Right. So I would like to, since SYK people discussed a lot in the literature, let me just state the result for the SYK then, and then I'll talk about matrix models, because I think that's a sort of more. So in the SYK model, then in the SYK, or even let's say we consider the SYK dots over just a finite dimensional Grassmann integral. Okay. You can do it in SYK, but let me just, for simplicity, stick to this thing. So we integrate over some Grassmann size, and we have some couplings J, and they are drawn. J's are drawn from a Gaussian from a Gaussian ensemble, then this sort of description, this sort of manipulations give you the answer that in the SYK dot, the approximation that we get becomes this A. So the first term is the usual wormhole like term that people describe, but the second term is the half wormhole, and these manipulations they give you this result. Is that the result is that you take the partition function, you consider it at complex couplings where the real part are the fixed couplings that you started with on the left hand side, and then you average over the imaginary part of the couplings. And in SYK, you can do this explicitly, and at least under the this psi integral, and the result that you get, it's something of this sort, and well, doesn't matter too much for now what are the details, but there is some, I just wanted to say there is some explicit formula that you can write from this, and big capital A's refer to ordered sets of Q indices, and this answer turns out is precisely what Schenker, Stanford, and Yao found in the from this G sigma description that we now reproduce from here. I didn't give you much detail about how you derive this, because for the interest of time, I would like to say more how it works in exponents. But this is a.
But somewhere there is a step where you assume that the little j is typical, or maybe we'll see that step in your.
Yes, well, that step is just is more to justify this approximation. You compute the difference, and you compute the variance in this ensemble, in the same ensemble. Yeah, in the same ensemble that small j's are drawn from the same ensemble as j's.
I see.
So this is the result, and you can also write this formula more generally in the SYK model. It will be a little more complicated, but it's essentially on the same sort.
And Jbar squared in the last term there is what?
That's the average of j squared in the Gaussian ensemble. That the all couplings in the SYK model, they are independent, and their average is this Jbar squared, which is taken to be this standard.
But your model just has a single coupling little j, so there should be a way to define Jbar in terms of.
Oh, sorry. There, I just didn't write the index. So there, the small j's and sigmas refer to this set of couplings.
Right. But your fixed coupling theory has Jbar is the average over these fixed couplings. Is that the statement, or what is? How do you define, like, the thing on the left-hand side of this equation?
Yeah.
Only involves your fixed coupling theory, right?
Yes.
So, and on the right-hand side, there's a Jbar. So how is that?
Well, Jbar is just this number. Oh, Jewish. But this equation is true when you take small j's and you draw them from from this ensemble. Then for a typical choice of this small j, that equation will be true. And so yeah, it's this.
But you're saying something a bit more than just averaging this equation over small j, because then it would be trivial, right? If you average this equation over small j in the ensemble, then both sides
They
are
get
the same.
0, yeah. Yeah, the interesting part is that you compute the variance.
The
The
variance,
variance
I
is small.
I see,
It's small.
okay.
Yeah, that's the non-trivial.
Okay.
The variance is.
May I ask a question?
yeah.
So in what sense is there a factorization puzzle being solved if all of it is sort of approximate? Like the left and right, there's still subleading terms in which the right-hand side is just not equal to.
That's right, yeah.
So you're imagining like in gravity, you'd need to sum up infinitely many saddles or something like that to see this full factorization, or what is the statement?
Right, so I think the interesting part, at least to me, the most interesting part of the paper by Schenker, Stanford, and Yao, is not really that there are terms that resolve factorization, it's this fact that they have a large n description. So I think that's what makes it interesting for gravity, is that at large n, we still have a factorization problem, and there's a at least in this sort of somewhat weird sense, there is a semi-classical description of this extra term. That you do not need to know everything at large n to resolve factorization, but it's enough to have this. Yes, that's a good point. I think the most interesting part is that there's a large n description of this. But in principle, at least in this SYK dot model, we can continue this expansion at large n. Actually, that's what I've done in like my paper from last spring, but I considered some corrections to that. Okay, so let's now go to matrix models. So in the matrix models, so you consider this partition function, just the usual partition functions, where you draw the Hamiltonian from some ensemble, and we can again consider here by either left or right systems. So here again you can play the same tricks, and the formula you get is that you have you get a formula of this sort where you have an extra integral over the matrix over Hermitian matrix sigma. Not right, and let me write it in a slightly different way. Right, and there's z left, z right, and this w wh, which I average over h, and there's and by w, I know this is this exponential gravity because it will appear many times. Just this exponential, and I multiplied and divided by w, so that's that formula. And again, right.
Is there also a potential piece maybe?
The potential is in this averaging, yeah. So this averaging, also this averaging, which I will sometimes read the subscript of, is an integral of h with with some potentiality of h, which you choose. Okay. Right. So now you do the same kind of approximation that we would like to take. You take the average, and you take and you take this linked half wormhole term, and okay. And now we would like to compute this formula more explicitly and show that the variance is actually small. Right. So then the approximation we get, right. So roughly speaking, we have a formula like that, where this phi of h naught is this integral. Let's say I'll set the temperatures to be the same on the left and on the right, and it's just okay. And what we would like to show is that we would like to compute essentially the variance of this difference. So error squared, which we would like to then average over h naught and show that it is small. Okay. Right. And if you compute this quantity, if you just do this expansion, well, you take a difference of the left and right hand sides and take a square, then the formula that you get to leading order at large m is that you have some sort of more standard contributions that you know how to compute in matrix models, and then there is a more interesting piece where you have the average, these averages of this linked wormholes. Okay, so here, here on the right hand side, in these terms, yeah, I mean the average over each naught.
So angle brackets always means integral over h?
Yes, so angle brackets always mean this integral with the potential.
Right, and so if I stick in a w, then this becomes some function of the matrix sigma?
Yes, yes, that's important. That's, yeah.
Okay, and so you have some complicated rational function of sigma in some sense?
Yeah.
And you then want to integrate over that?
Yeah.
And how do you find a saddle of that awful thing? Or do you bother? Could you give some intuition as to how the last formula you wrote is derived?
So it's derived from this approach, but maybe you're asking about something more explicit computation of this integral.
Yes.
And what I will hopefully have time to show you is how to compute it in the Gaussian case.
Okay.
In the more general case, it's very interesting. I do not know exactly how to do that. There is actually an exact computation of that in terms of orthogonal polynomials by Zinjustin, but I have not been able yet to make sort of a large n, something simpler at large n from that. But at least in the Gaussian case, we will see that it's. Okay, so the goal is to compute this error and show that it's small. Right, so the basic object that we would like to compute in the matrix models now is the average of this z times w, and the average, well, let me start with w, is the average of this exponential and the average of the partition function in the presence of this external. Let me, from now on, to actually make some explicit computations, let me from now on to consider just the Gaussian ensemble. It'd be very interesting to generalize this to more general matrix models, but at the moment, especially for the purposes of the first look, it's enough to have a Gaussian matrix model. And so the average, well, the average of W is very simple to compute. It's just a Gaussian integral, right? So W, I remind you, is this exponential of sigma trace of sigma h. So so the average so the Fourier transform of the Gaussian is a Gaussian. So that's just a trace of sigma squared. And the more interesting quantity to compute is this object. So this object you can think of as a conventional matrix model ensemble, but in the presence of this coupling to an external field. And things like that people studied in the 90s for some other reasons, but there is some techniques are known how to compute such things, and at least in the Gaussian case, people like Brezin, Hikami, and Z did this computation, and also is interesting in others. And so so the answer to this question, so in the Gaussian case that we now consider, you can actually compute this thing exactly, right? So just to start, let me briefly tell you what you roughly do. Okay, so h squared plus L trace of sigma h, and you would like to compute the this thing here. So the rough idea of the computation is that now when you diagonalize the matrix H, now because of this term, in this term you get dependence on the unitaries. And there's two factors of the unitary matrix. But it turns out you can still compute the unitary integral. It's called Harish-Chandra-Jbar integral, and you can do it exactly for this integral. And then the answer is relatively simple. It's just some determinant of some matrix made out of eigenvalues of sigma and h times some van der Waals and so on. And so then you again reduce to the eigenvalue problem, and that eigenvalue integral, actually in this Gaussian case, you can compute exactly. And the answer is the following. So the answer, which in this form was written first by Kazakov, is given in terms of this contour integral. So we have an integral over u, and we have a determinant, and the contour goes around all the eigenvalues of the matrix I sigma, so it picks up all the poles from this term. And it turns out so then you can kind of see from here that it's going to be a sum, and each term in the sum is some product over eigenvalues, and that's roughly arises from the van der Waals in this formula. So that's a known result. And for our purposes, it's enough to consider the large n approximation. And at large n, you can expand this determinant, and you get a resolvent in the exponential. Okay. And in fact, if you you can also check that if you set this sigma to 0, then the resolvent becomes 1 over u. And if you take this integral, you reproduce the standard result from the Gaussian matrix model. So it's sanity to check, but this is an exact result for any matrix sigma. And so now the formula for the linked half wormhole becomes as follows. So you have two, because there are two objects like that. So we have two integrals of you left. Right, sorry. Yeah, I should go back slightly. Yeah, so we need to stick that into that formula. First of all, these other three factors, these stuff outside of the integral times the exponential and average of w, it turns out that they combine into a Gaussian, and you get a right, and you get something like sigma plus h naught, that you get a shifted Gaussian. Right, and then you have you need to insert that this formula. So if you now shift the matrix sigma, this integral, and this formula, then the result that you get is some double integral. And you average. So here we shift this matrix such that this thing is some matrix delta sigma, and then you get these resolvents that involve the sum of two matrices. Sigma of units, and the sigma integral, it just becomes an averaging with the same Gaussian ensemble. So you get a product of these two exponentials of resolvents, and you average over Gaussian ensemble in this shifted variable. Delta sigma. So I am definitely out of time, but let me
I have like 5
say,
minutes.
I
I have like 5 minutes.
I started late,
Yeah.
right, that's right, okay, good. Okay, so yeah, right, so you get this kind of formula where you have these averages over these sort of imaginary parts of the Hamiltonian equation. So that's similar to the SYK case where we average over the imaginary part of the couplings. And this formula allows you to compute now the error. So to compute the error, we need to compute two objects. We need to compute average of phi squared and average of phi z left, z right.
And these integrals, the u's are like eigenvalues of the matrix?
U is a contour integral and it goes around the eigenvalues of this matrix.
So it's the control parameter for the resolving.
Right, and so now what we would like to compute is the variance, and we need to do that, we need to compute the average of phi squared over h naught. And so you use that formula. Then you get a product of 4 exponentials of this sort, right? Where you average over this delta sigma. Then in the second factor, you will have a similar thing, but with resolvents depending on a different delta sigma. Let's call it delta sigma prime, right? And so on, where you average delta sigma prime. So just imagine writing the same thing again with some sigma prime. And then in the end, we also want to average over h naught, right? So this sort of looks complicated, but you can actually compute this this average if you these are, well, you know, these are algorithms. Yeah, and to compute this kind of average, you need to compute averages over all matrices, delta sigma prime, and h naught. And the way you do that is in kind of 2 steps. You first average over h naught with delta sigma and delta sigma prime fixed. And then you average over delta sigma and delta sigma prime. So in the first step, when you take this product and you average over h naught, so this problem is what people sometimes call a deterministic plus random Hamiltonian. So in this first step, you average over h naught, so h naught is random, but the matrices delta sigma and delta sigma prime are fixed. And this kind of problem also is known, and people studied correlators of resolvents. Baurzhan, Mukhametzhanov, and Z studied this kind of correlators. And the answer for them is very similar, or computation for them is very similar to the standard 2-point function of resolvents. So if you're familiar with their computation, they compute summing toothed diagrams, and kind of you have like 2 circles, and you consider only correlations between the sides, and so similar computation goes through there, and you can find the formula which depends on delta sigma and delta sigma prime, and at the end you can do the average over sigma and sigma prime as well, and the result that you get is that these averages of phi squared and also of phi z left, z right, that at large n, they give you two terms. At large n, they are the same as the sum of these two averages. Okay. Where by this average, at least in this, in the matrix models, by these averages, what I mean is that we take an integral with standard factors and these density correlator, where this density correlator is computed by sort of standard universal result in the matrix models. That's that's known in the matrix models. Right.
But basically, in some sense, what you're computing is higher point functions, right? Of these density correlators. That's kind of your error. One think of what you're doing as computing higher point functions of these density correlators. Like you're asking how close. You know, you're computing z of j minus the average, or z of j squared minus the average z of j squared, and you want to know the variance of this. Say that looks like a 4-point function of densities, right?
Yes. Well, here it's a 4-point function because you take, this is the formula for the just average of the level, right? And then taking the square.
Yeah.
But here just the claim that is that if we take this wormhole contribution phi and we compute the variance according to this formula of the error. Yeah. We need, well, these two terms we know from a formula like that. Right. And these two terms we would like to compute, which I roughly described here. And if you do this computation, you find that these two quantities are given by the sum. And so you see from this formula now that to leading order at large n, they cancel out. It means that this error is subleading at large n. So there will be corrections suppressed by 1/n squared. But this formula now shows that this error is small at large n. That they cancel out.
Is this saying more than just like, you know, if I look at z of j, so it has, z of j has some average which is 0 and some variance which is the usual spectral form factor. And then it has higher moments, right?
Yeah.
Is this just saying how higher moments scale compared to the first moment?
No, it's
something more.
That. Yeah,
Okay.
if you just if you don't include this half wormhole term, the variance will be large and comparable to the form factor itself.
Okay.
But if you do include this half wormhole term, the variance is small. And here I assume that average of z is squared, or I subtracted it out or went to long Lorentzian time, so I don't really care about average of z itself. I care about average of about the average of z squared and its variance.
I see.
Okay, well, I guess I will. Let's see. So right. Right. So let me, I guess, just briefly summarize. Here we sort of presented an approach which I think is a little more general than the G sigma action, and it seems like this kind of manipulation, this kind of construction you can do in any sort of theory with an ensemble average. At least you can write down this approximation not sure if it's always a good approximation, but maybe. And in particular, in matrix models, we showed, I guess, we showed that at least in this Gaussian case, it's indeed a good approximation, and you can do all the computations exactly. But the interesting questions, the interesting question, at least for me, is how to do this computation maybe in a more principled way. I guess here we sort of use some exact results in Gaussian matrix models. But it'd be interesting to know how to do this computation in sort of more generic matrix models, perhaps using some exact results that are known by Zingerstein or something of that sort. So that's one.
But if you start with a quantum field theory, shouldn't a Gaussian matrix model be a good approximation for it?
Gaussian to what approximation?
To let's say your system is some quantum field theory that is local in space and there's some large volume. Then wouldn't you expect that the Gaussian approximation is like most things aren't most things described by random matrix theory?
Well, are you thinking just about the fact that the hydrogen spectrum looks like a random?
Right, like that. If you have some extended quantum many-body system, then many aspects of it is very well described by Gaussian.
Well, some aspects, like short distance correlation,
right.
of densities.
But this very late time stuff that you're talking about is one of these. So I guess, you could say that what you're saying, one way to say what you told us is that this is a prediction from random matrix theory, and so you could say, oh, it's another, like if your system is described by random matrix theory, maybe it's a more fine-grained prediction than things like the ramp and the plateau, but it's still a kind of consequence of random matrix theory.
Well, yes, but even the ramp and the plateau are more universal. Not just in the Gaussian case.
Maybe a way of asking the question is, so a lot of the structure that people have been focused on is basically just the local structure of the eigenvalue correlation functions. So you don't, for that you just need to know sort of like what is the short range properties of nearby eigenvalues. So is there anything in what you're doing that cares about correlations between eigenvalues that are further away? Or is it all just this like short range Gaussian, eigenvalue repulsion?
I would guess not, because you're talking about very late time stuff. So it's gonna kind of concentrate you on very short range.
Right. So the reason I think it's interesting to consider more generic matrix models is that they have they're dual to minimal strings, at least for some cases. If you take a double scaling limit and so on. And so the ultimate, sort of the goal of this whole business, I guess, is to understand this in gravity. And the question, which I'm not sure how sensible is this, but the question I have is whether we can, first generalize the potential, but then also to introduce some kind of double scaling and see if this is in any way is related or can be done in the minimal string, or is the limit of the minimal string JT gravity, but plus some other degrees of freedom that are described by this matrix sigma. So it's more like it's going to be more like some kind of two matrix model, I guess. The one matrix is this H matrix, but then you also have this sigma matrix, and then you have some coupling between them. And in fact, the coupling between them, which is trace of sigma H, it looks somewhat like it looks like the chain matrix model, but with an imaginary coefficient. And I'll stop here. Thank you.
Any more questions for Bauer? Yes, people already asked.
I have some more questions, but we can do it after.
Let's thank Bauer again.